In this lecture, we'll be discussing sedimentary rocks in more detail, along with sedimentary environments. We'll also, at the end, briefly discuss fossils. For the first part, we're going to talk about the sedimentary rock life cycle, where we go from the generation to sediment to the formation of sedimentary rock, look at clues for determining the environment in which the sediment that composes the rock was deposited, look at different types of sedimentary environments, and as I said, we'll discuss fossils briefly. First, we'll look at the sedimentary rock life cycle. We go from sediment, loose unconsolidated material, to rock. Well, the first part of the sedimentary rock life cycle is that sediments have to be generated, have to be produced. And how sediment is produced is starts with rock being exposed at the surface. So when bedrock is exposed at the surface, it is broken down, which we'll talk about next. It's weathered. You can see this is bedrock. This is sedimentary rock, and we know it's sedimentary rock because we can see how it is deposited in layers. And you'll see that is a feature of sedimentary rock, it being layered, because sediments are deposited in layers. And all this material down here, this is all pieces of rock. This is sediment. So this is the bedrock, and it's being broken down into sediment. And this is all sediment. Now, sediment takes a wide range of size, from large chunks, boulders, to very tiny pieces of mud and clay. So after rock is exposed to the surface, it's then sediments are created by the bedrock being weathered. Now, there are two different types of weathering. There's mechanical weathering, which is the physical breakdown of rock, and chemical weathering, the chemical breakdown of rock. So agents of mechanical weathering include rain, wind, glaciers moving across, grinding, breaking rock apart, vegetation, the roots of vegetation growing into cracks and heaving those cracks open, breaking pieces of rock off. The freeze-thaw cycle of water is a very common source of mechanical weathering, where water will fill in a crack, it'll freeze, the water expands and heaves the crack open wider. Eventually that busts pieces of rock off. It's actually the same process that causes potholes in roads. So mechanical weathering is the physical breakdown of rock into smaller pieces. Where chemical weathering is the chemical breakdown of rock. That includes water dissolving rock and acids, like acids that are from rain, acid rain, sulfuric and carbonic acid, those decomposing and helping dissolve rock into water more quickly. So rock is produced when it is exposed to the surface by the weathering, either mechanical or chemical weathering. So looking at this photo, at what location are the most sediments originally created? We see A is the face of this mountain. B is the base of this mountain here, and it's actually a pile of what looks like to be sediment. And C is this stream bed, stream channel, which we can see there's actually sediment being in this stream channel, these pieces of rock right here, sediment. So where is the rock, where is most sediment originally created? In other words, that question is asking, where is the most bedrock being weathered? Well, the answer is A. And why is it A? Is because this is where the bedrock is exposed and it's being broken down, being weathered. At B and C, we find sediment. The bedrock is buried beneath that sediment, so it's in a sense protected by those layers of sediment on top of them. They're not being, it's not being weathered or broken down into sediment. So most sediment is generated at higher elevations, because at higher elevations, bedrock is more exposed. And then that sediment is created at higher elevation, and then it finds its way, as we'll talk about, is transported to lower elevation, such as these two locations, B and C. So once sediment is created by the weathering of rock, usually at higher elevation, it doesn't have to be as high as the big mountain we saw in the past slide. It could just be the relatively high point of elevation, whatever the topography is. After sediments are generated, they are then transported. There's 3 different ways in which sediments can be transported: running water, wind, and glaciers. Running water is the most common mode of sediment transport. And with running water, the stronger the currents, the larger the particles of sediment that can be transported. So large currents that are very strong, have a lot of energy, they can move all different sizes of sediments, large chunks of sediment and tiny pieces of sediment. Where very slow moving water, like this muddy stream channel, the top left, it's just moving slowly. It's only carrying mud. And you can see this stream channel, it's moving along sand with it. Okay. Running water is the only way to transport dissolved minerals, which is one type of sediment. And whenever running water transports sediment, the further the sediment is transported by the water, the more rounded the sediment becomes, because the grains of sediment get worn and weathered themselves, and so they become smooth and rounded. Glaciers can move sediment of any size. They kind of act like a bulldozer, just pushing sediment in front of them and dragging sediment along their sides. And whenever glaciers deposit sediment, it deposits poorly sorted sediment. So if we'll talk about sorting, it drops boulders and little tiny smaller cobbles and little tiny pieces of sand and everything all together. And like running water, the further that the glacier transports the sediment, the more rounded the grains of sediment become. And finally, we have wind. Wind can generally only transport sediment that's the size of sand and smaller. And like running water and glaciers, the further the wind transports the sediment, the more rounded the grains of sediment become. Though sediment deposited by wind is usually fairly rough because it's usually not transported that far. Here you can see sand being blown off of the west coast of Africa over the Atlantic. So whenever sediment is deposited by one of those 3 modes, running water, glaciers, or wind, it could be have different variations of sorting. Now, the sorting of sediment is how uniform the grain size of the sediment is. So very poorly sorted sediment is sediment deposits with a large variety of grain size. So you have very large pieces and medium size and small pieces, all mixed in with each other. Poorly sorted is there's just a little bit more uniformity in the grain size, but they're still pretty varied. Well sorted means that the range of grain size of the sediment is not that significant. Most grains of sediment are within a small range. And then well sorted sediment, it was never, almost all the grains of sediment are the same size. It's very well sorted. So how do we get these different types of sorting? Well, in general, the more energy involved, the more poorly sorted the sediment is. So for example, a glacier or fast moving water, if you think fast moving water coming down the side of a mountain that's steep, those are high energy and they are going to deposit poorly sorted sediments. Where very slow energy, like some wind or slow moving water, they can only transport smaller particles of sediment, and so they deposit that sediment is well sorted. So the more energetic the water is, the more poorly sorted the sediment, and the slower the water, less energy has, the more well sorted the sediment. So you'll notice at a beach, you have fairly well sorted sediment, often with sand, because by the time the the rivers get to the beach, they're moving fairly slow. So then we have angularity and sphericity. So I'm going to focus on sphericity, angularity, of how angular or rounded the sediment is. Angular sediment is sediment that has sharp edges and points. And then subangular, which is a little bit more smooth. Subrounded, it means it doesn't have any sharp edges or points, but it's not, it's not a perfect, doesn't look like a sphere, perfect sphere yet. And well-rounded is whenever the sediment looks almost like a sphere. So the angularity of the sediment gives us information about how far the sediment has been transported from the source, the bedrock it was weathered from. The more angular the sediment, the shorter the distance it has been transported. And the more rounded the sediment, the longer the distance it's been transported. So going back to our example of a beach usually has fairly smooth sediment, right? The sand doesn't feel very coarse. Not all the time, so most times it doesn't feel very coarse. Why? Because that sediment is fairly well rounded, because it's been transported a substantial distance by rivers before being deposited into the ocean. So looking at the same picture we looked at before, at which of the locations are the most sediments being transported? Well, the correct answer is C, because we have running water, right, that's transporting the sediment. You might think, like, well, how is this water transporting these large boulders? Well, this water, as we see it here, is not. This water that's flowing through there might be transporting some mud. It's definitely transporting some dissolved minerals, but as far as pieces of rock, it's maybe transporting some mud or sand. But in the springtime of the year, when there's a lot of rain and there's a lot of snow melt, this river, this stream channel, it is roaring. The water is roaring through it because there's so much water being drained out of the area that those large currents, that high energy flow, is able to move and transport these larger particles of sediment. So once sediment is transported, it's then deposited or dropped somewhere. And then an environment in which sediment is deposited is known as a sedimentary environment. Now, there is a large number of sedimentary environments, include glacial environments, right, where glaciers move and deposit sediment. You have stream channels, you have lake beds, deserts where wind deposits sediment. You have alluvial fans at the base of mountains, lagoons, the shallow seafloor, continental shelf, organic reefs, like coral reefs, islands, the beach, river deltas where rivers dump sediment onto the seafloor. Then you have deep seafloor. Then you have these submarine fans where currents flowing down the seafloor bring sediment and deposit them. So we have a lot of different types of sedimentary environments. And notice something that most of them have in common is water, right? Most of them involve water because water transports the most sediment. But each sedimentary environment has generally, in most cases, a characteristic sediment. As I said before, you think of beach, what do you think of? You think of sand. If you're thinking of an organic reef, a reef is built out of the structures of organisms. We have calcium carbonates. You're going to think limestone. Tidal flat, it's muddy. You're going to think mud turns to shale, and so forth. A desert, you think sand, right? It's going to form sandstone. Alluvial fan has different types of rock. So each sedimentary environment has generally a characteristic sediment that is deposited there. So for example, here we can see this beach, right? You see the nice sand at the beach. Or this river delta, you can see this is all mud being deposited in this river delta. Okay, so this is the Mississippi River. It's flowing, and you can see it's actually brown because it's so much laden with so much mud. And whenever it dumps into the Gulf of Mexico, it's depositing all that mud. So how do we go from the deposited sediment to sedimentary rock? Right? So what we talked about in our last lecture, the process of lithification, how unconsolidated rock is turned into consolidated rock. That involves the compaction of sediment and then the cementation of sediment. Well, sediment is deposited often in horizontal layers. Most types of sediment, especially clay. That's because they're deposited by water. Most of them are deposited by water. And how does sediment settle out of water? It settles out of water into horizontal layers. And then once that sediment is in horizontal layers, then it lithifies and forms sedimentary rock. So whenever you find sedimentary rock, it's usually layered because the sediment it formed from was layered. And that's what we can see here in the walls of the Grand Canyon. We can see these layers of sedimentary rock. And so here you can see those layers identified by these black lines. And we call these layers beds. So these are beds of rock. And that's where the term bedrock comes from. It's rock that's still in the bed. So this is all bedrock right here, all along the rims, because all along the walls of the canyon, because this rock is still in the bed in which it formed. So once sediments are deposited in horizontal layers and then turned into rock, with the process we mentioned, lithification, where the sediment is compacted by the weight of additional sediments deposited on top of them. And then the minerals dissolved in water that seep through the sediment, they precipitate out and cement grains of sediment together, lithifying them together, forming the consolidated sedimentary rock. So for example, here you can see some unconsolidated sediment. It's very poorly sorted, very rounded sediment. If this would be lithified, it would form sedimentary rock that might look like this. Right? Where you see all of the sediment is now consolidated. It's compacted and cemented together. So you find very old sedimentary rocks in Arizona. What can you determine from this? Is it A, that sediments were deposited in Arizona in the past? Is it B, sediments are currently being deposited in Arizona? Or is it C, sediments were deposited in Arizona in the past and they're still being deposited today? A second to think. Well, the fact that these sedimentary rocks are very old, that means that they formed from sediment that must have been deposited a long time ago. Now we find them in Arizona today, like the ones we just saw in the walls of the Grand Canyon. And because that sedimentary rock exists there, it tells us that at one point in time in the past, sediments had to have been deposited there, or else that sedimentary rock would not exist. So the presence of that sedimentary rock tells us that sediments were deposited in Arizona in the past. They, however, do not tell us anything about present day, right? They are a snapshot of the past. They don't tell us the presence of sedimentary rock in a location doesn't indicate that sediments are actively being deposited there now. So the correct answer is A. They tell us only about what was happening in the past when that rock formed, and that was that sediments were deposited in Arizona in the past. So rocks often tell you about what happened when they formed. They don't tell you too much about what's going on today, except whenever those rocks are being weathered, see what processes must be occurring to weather or alter that rock. So we can see all these layers of sedimentary rock in Arizona. This rock happens to be the reddish brown stuff. This is sandstone. Sandstone. The brown layers is shale, and the lighter colored layer, that's limestone. So think, what sort of environment was there? Sand, mud, and the remains of the calcareous exoskeletons of organisms like coral and clams and so forth. But if you're thinking the Atlantic Ocean, you're correct. For several hundred millions of years, this portion of the United States was a shallow ocean in which all these sediments were deposited and were later lithified into sedimentary rock, which are now exposed by the Colorado River and the Grand Canyon today. So to review the sedimentary rock life cycle, the sediments are exposed. So bedrock is exposed to the surface where it's weathered by chemical or mechanical weathering. It's broken down into sediment. That sediment is then transported to lower elevation by glaciers, running water, or wind. It's deposited where it gets buried, compacted, cemented, and lithified. So that is the sedimentary rock life cycle. So I'm going to look at some clues for determining the environment in which the sediments that form the rock were deposited. So if we find sedimentary rock in beds, like we see here, you can see these beds of rock, horizontal layers. That tells us that it was often deposited by water, right? So this was some sort of environment with water in which a sediment was settling out of the water into these horizontal layers. However, if these beds are not horizontal, if there's beds that cross each other, so you see these beds come up here, and there's a bed that cuts across it there, that cross bedding indicates that it might be a desert from dunes, formation of dunes. Other clues might be structures preserved in the rock itself, like these ripples. So you can see these ripples in the sandstone. Ripple marks are usually formed as a result of water flowing over sediment, such as a beach of an ocean, a lake, or a river. And so sometimes what happens is when these ripple marks form, maybe the tide goes out or there's a lack of rain and the water level in the lake or the river subsides, and the sand can dry, and those ripples kind of get loosely preserved in the sand because, in the water there's some minerals, and those minerals crystallize out as the water evaporates, as the sand dries, and they kind of hold the sand together a little bit. It doesn't lithify the sand because it's not compacted, right? But what happens is the next time the water rises with the tide, or if there's some rain that causes the level of the lake rise, a new layer of sand is deposited over top of those old ripples. And then later, if those layers of sand get lithified, then the boundary between those layers exists those ripples. And so those ripples form in between the layers of sedimentary rock. This is also how footprints are preserved too, or if you can imagine if an animal walked across this beach and left its footprints there, and then sediments are deposited over top of those footprints, they would be preserved in the rock as well. So ripples can provide a clue for the environment, indicating that water was flowing over the sediment. We see mud cracks, tells us that there was fairly slow moving water that was depositing mud, maybe in a lake bed, and then that water evaporated and the mud dried, forming mud cracks, and then later water flowed over, depositing a new layer of mud over the dried up layer, preserving the mud cracks. So now we're looking at the different sedimentary environments and some rocks that form from the sediments deposited in those environments. So we went through these environments before, but there's a large number of environments. We said most of them deal with water. So first we're going to look at glacial environments. The glacial environments are usually high altitude environments because glaciers form, as we'll talk about later in the course, high altitude valleys, mountainous valleys, or at high latitude, like near the poles, Greenland and Antarctica. But when the glacial ice moves, it transports all different sized sediment and deposits very poorly sorted and well-rounded sediment, like you can see here. This type of sediment is also deposited at the base of mountains, where water flowing quickly down the base of the mountain, it begins to slow down once it reaches the the flat land at the base of the mountain and then drops the large sediment it was carrying. And so we get fairly, some poorly sorted, well-rounded sediment depositing what are known as alluvial fans at the base of mountains. Well, if this poorly sorted, well-rounded sediment is lithified, it forms the clastic sedimentary rock conglomerate. So there you can see a large outcrop. Outcrop is where the bedrock is exposed. Large outcrop of conglomerate. You can see it's just poorly sorted sediment that's well-rounded. So anytime we find conglomerate, it's often either an area that has been glaciated, or it's the base of a mountain, or basically anywhere where water is flowing very quickly, and depositing very poorly sorted sediments. Now, a landslide is whenever rock moves just a short distance under the force of gravity. And so it's poorly sorted, but it's very angular. It's not well-rounded at all. So these deposits from a landslide will form a different type of clastic sedimentary rock. It's similar to conglomerate in that it's poorly sorted, but it's different in that the particles of sediment are angular. They're not rounded. And this forms the clastic sedimentary rock Breccia. So Breccia is poorly sorted, angular sediments. You have a desert environment where sand is being transported and deposited in dunes. And that can form sandstone. And so, as I said earlier, sand deposited by wind is usually not as rounded as sand deposited by water. So the sand is more coarse. So a coarser sandstone might be suggestive that it was deposited in the desert. Or the beach, it deposits more well-rounded sediment. And so those sediments could form smoother sandstones, and those sandstones could also have ripple marks in them from the water flowing over the sand. A river delta, where often mud is deposited on the seafloor. That mud accumulates over time. And also in lake beds, where you have water that's not moving very fast, mud is deposited at the bottom of a lake bed. And the mud in the river delta or the lake bed it lithifies to form shale. So shale is made up of very fine sediment. So this is also a clastic sedimentary rock. So far, conglomerates, sandstones, and shales are all clastic, but it's very fine because it's made up of mud, lithified mud. So if we find shale, there's likely a muddy seafloor, or maybe even like kind of a swamp along the coast, muddy swamp, or a lake bed, anywhere where mud is deposited. Quickly, I grew up in western Pennsylvania, and about 300 million years ago, during a period of time known as the Pennsylvanian, that Pennsylvania was near the equator, and in the coast there was a coastline running right through Pennsylvania, and there were these tropical swamps where a bunch of mud was deposited. And we'll talk about this later in the course, what was going on during this time in North America. And so that mud deposit formed shale, and in that shale was fossilized vegetation like ferns, and every now and then you might find a fish. So there were outcrops of shale around where I lived, and I would pull out chunks of the shale out of the walls, as you can see here, and rip apart the beds of shale, and look in between the beds and find fossils of ferns and fish. And that's one of the reasons why I got into geology and earth sciences, because I just found it so fascinating that I was pulling out of the walls of this rock. I was pulling out these pieces of rock and ripping them apart and seeing snapshots or remnants of organisms that lived on this planet before I did. Before any of my ancestors, before people, before even Yeah, before most mammals were just starting to maybe come on the scene at that time, but such a long period of time ago that the Earth was here. There was life was flourishing on this planet, and it's a whole different world. And I just found it so mysterious and interesting. And so, these sedimentary rocks are all historical environments. They tell us about these historical environments which we can learn from, which is just so interesting. A river valley has different types of sediments deposited in it, different stages. So here you can see this river valley has very poorly sorted, well-rounded sediment. This would lithify to form conglomerate. This river valley is depositing sand, which would lithify to form sandstone. So what happens is as during the spring of the year, when all the snowfall melts and all the rain falls, the water is rushing through here. It rushes down the slopes, steep slopes of these mountains, and it's roaring through here very fast. And that's why it's able to transport and deposit this very large pieces of sediment. But over time, what happens is these mountains, they weather away. And so if this is the current slope of the mountain, over time, it's less steep. All these mountains less. So this mountain back here might be like that, and this mountain goes like this. And because these slopes are less steep, the water flowing through here is flowing through here more slowly. So it can't transport these large particles of sediment. Where it can transport is sand and mud, and so it starts depositing that sand. So later on, as these mountains weather away and are not as large and steep, the water flowing through here will be moving more slowly, and they'll start depositing sand on top of this conglomerate. And as even more time goes by, these mountains will weather away so that they're barely mountains at all, right? And so the water will be moving through here very slow enough it can't even move sand. It just moves mud, and mud will then be deposited on top of the sand. So we'll have this layering of different types of sediment: conglomerate, and then on top of that sand, and on top of that mud. And why the type of sediment being deposited changes is because the topography around the stream channel changes. The mountains weather away, so they're not as high, they're not as steep, and so the water flowing down them doesn't pick up as much speed, it's not flowing as fast, and so the water has lower amounts of energy moving through the stream channel as time passes. And so we can find not only individual layers of rock, but multiple layers of rock, different type of rock deposits on top of each other, which tells us about how environment changed with time. As you can see here, we have conglomerate down here. So conglomerate, sandstone, and shale. You can see the very large pieces. It's poorly sorted. There's tiny pieces. So it's poorly sorted, well-rounded. This is fairly well sorted, right? You can see the grains of sand. This is very well sorted, where it's hard to see the individual grains. It's very well sorted, and it's very tiny grain size, so it's hard to see the individual grains of sediment. So this suggests that this was deposited in a river valley that was once in a mountainous area, and over time those mountains weathered away. So this sequence of sedimentary rocks, from the conglomerate to the shale, tells us what happened over time. These mountains weathered away. Then cross-bedding, which we referenced before, forms as a result of dunes. So how sand dunes work is sand is blowing. The sand pretty much consistently blows in one direction. And as the wind blows sand up the slope of the dune, the sand then drops down the tail end, or the downwind end of the dune, and then so a new layer of sand is deposited. Then next windstorm comes and it blows more wind. Blows more sand. It's then deposited. And then the next windstorm comes and deposits even more. So each deposit of sand forms a new bed. As you can see, these beds of sand that have been deposited here. Then a new dune starts to form, right? Then there's bedding between the old dune and the new dune. So you have the bedding within the dune, like these beds, and then you have the bedding between dunes, like this one right here. So it causes these beds that cross each other. As you can see here, you have the bedding going this way, then you have the bedding going this way. So this would be the bedding between, in between dunes and inside of dunes, and this is the bedding between dunes. Okay, these red lines illustrate it better. So, so this is the bedding of layers of sand inside the dune. So multiple layers of sand deposited inside the same dune, and this red line and this red line indicate beds between different dunes. So also in deserts, if we have some water, it often vaporizes. And whenever water vaporizes, the dissolved minerals are left behind and they form chemical sedimentary rocks. So chemical sedimentary rocks are often rocks we find in arid desert environments as well, along with cross-bedded sandstone. So here you can see these chemical sedimentary rocks forming. This is a salt flat. This is just all salt that's been deposited. Now, salt, I don't strictly mean table salt, sodium chloride. A salt is any solid that's able to be dissolved in water. And so calcite is a salt, sodium chloride, obviously table salt is a salt. There's other salts like magnesium sulfate, you might have heard of as Epsom salts. So those are all different types of salts. So this is minerals that are dissolved in water. So we call these chemical sedimentary rocks, often call them evaporites, as we talked about in the last lecture, because they form from the evaporation of water. So here you can see a salt deposit. Here, this is a salt mine, a table salt mine. So the floor, the walls, and the ceiling, this is all salt. Now the salt that you eat, table salt. And how this formed was there was once a shallow sea here that vaporized, evaporated. And as it evaporated, the dissolved minerals in it precipitated out, they crystallized out. And so it formed this layer of salt, which they mine. So whenever we have pure table salt, this is where we get it from. We have to mine salt out of the ground. Where sea salt is different because it has all different types of salts. We get sea salt by just capturing seawater and letting it evaporate. And we get all different types of salts, not just sodium chloride. You get calcium in there, there's magnesium, there's phosphate, there's all different types of salts. But the table salt, just pure sodium chloride, has to come from a mine because whenever a body of water evaporates, the different salts crystallize out at different times, and so they form layers. And so above this layer of table salt might be a different type of salt, and below it might be a different type of salt. But this layer happens to be table salt. So another environment is a swamp. And so in a swamp, we have vegetation growing amongst very slow, in fact, usually stagnant water that's not moving. And what happens is, whenever water doesn't move, it doesn't have oxygen dissolved into it. If you ever had a fish tank or you have a fish tank, you have a filter the water. And you usually, if I were to draw a fish tank up here, and you usually put the filter up top, maybe it goes down into the water. It pumps the water up, it filters it, and then it drops the water back into the tank. Why does it drop the water back into the tank? Well, because by dropping the water back into the tank, it kind of stirs it up. And that's what allows oxygen to dissolve into the water. And oxygen is important because animals need oxygen to live. And so the fish in a tank, they need that oxygen to be dissolved into the water. And so if the water is stagnant, if it's not moving, no oxygen is being dissolved into it. And not only animals need oxygen, but microbes that are aerobic. Aerobic means that it consumes oxygen. Aerobic microbes that break down or eat organic matter need oxygen as well, just like we do, because they're eating food or eating organic matter. Organic means living. It's organic molecule. It's carbohydrate. So these microbes, they're responsible for decomposition or decay. So whenever you have leaves decaying in the woods, or an animal dies in the woods and decays, how does it decay? Well, microbes and fungus eat it. That's what decay is. It's being broken down and eaten by microbes and fungus. And they need oxygen to do so. So if the water is stagnant and no oxygen is being dissolved into the water, what happens is the water becomes what's known as hyperoxic, or a condition called hypoxia develops, where there's very low oxygen levels in the water. And so because of this, the microbes can't decompose the vegetation. And so the remains of the vegetation accumulate instead of rotting and decomposing. And so in these swamps, we get these large, thick layers of dead vegetation accumulating, which are known as peat. And that organic material, that peat, if it gets buried by other sediments and compacted, it turns into the biochemical sedimentary rock coal. So coal is nothing but compressed and lithified remains of vegetation. That's why it burns, just like if you can burn leaves or a piece of wood. But this is very, very compact vegetation, so it burns fairly well. There's a lot of energy in coal to burn. That's why coal is also very dirty. You burn coal, it produces a lot of dirt because it literally formed in a swamp where everything accumulates. And whenever you burn it, a lot of that dirt gets released into the air. But it forms from ancient swamps. So ocean reefs, organic reefs, where the exoskeletons made of calcium carbonate of organisms like coral or snails or clams, oysters, so forth, they accumulate and they get buried, compacted, lithified. They can form limestone. In this case, this is fossiliferous limestone because we can see the visible fossils. Most of these fossils are snails. We'll learn snails are a type of invertebrate known as a gastropod. So you can see these snail shells. And this looks like a clam, which is a bivalve, another invertebrate. But you can see the visible cells. So this is fossiliferous. It's important. All limestone is made up of calcium carbonate, which is one calcium atom, one carbon atom, and 3 oxygens. So in seawater, calcium and carbonate, they're just floating around. They're dissolved in the water. And what these organisms do is they take in the water and they filter this and this out of the water, and they bond them together to form calcite. And they use that to make their shells or exoskeletons out of. So this stuff is literally dissolved in the water, and these organisms take it and excrete, and they bond it together and excrete it to make their shells. Then whenever they die and their shells or exoskeletons accumulate, it gets compacted and it lithifies to form limestone. So all limestone is calcium carbonate formed from the remains of organisms, calcareous organisms. Calcareous means calcium bearing. But some parts of the ocean where there's no reefs, no structures, there is calcium carbonate being deposited because in the surface of the water are little tiny organisms that are photosynthetic called plankton. And these plankton are microscopic. And some of them make exoskeletons that are made out of calcium carbonate. Whenever they die, exoskeletons, they settle to the sea floor and accumulate. Now, calcium carbonate is white. So whenever this calcium carbonate from all these exoskeletons accumulates on the seafloor, it forms this layer of white sediment. And this is known as a carbonate platform because there's so much calcium carbonate deposit on it. Now, if this gets buried by other sediments, compacted and lithified, it'll form a layer of limestone too. The difference is because these organisms are so tiny, they're microscopic, you can't see their individual exoskeletons. This is non-fossiliferous limestone. If you look under a microscope, you can see the structures, right? You can see the structures under a microscope. But if you had a piece of limestone in your hand, non-fossiliferous limestone, you can't see any of this. So these are the white chalk cliffs of Dover. Now they're made up of limestone. Why are they called chalk? Well, because chalk is calcium carbonate. It's limestone. They just crush limestone up and they pack it into cylinders and make chalk. We use limestone also to make cement. So cement is crushed limestone. We also use limestone in other items like you ever have an antacid like a Tums? Taste kind of chalky? Well, because it's chalk. It's calcium carbonate. We also use calcium carbonate in toothpaste to make it white and so forth. So calcium carbonate from limestone has a lot of uses. And so these white chalk cliffs of Dover, what do these tell us? Well, we know that this sediment, it's called calcareous ooze. This white sediment from the remains of calcareous phytoplankton. Phytoplankton that make calcium carbonate exoskeletons called calcareous ooze. So calcareous ooze was accumulating on the seafloor for a really long time. Then it was compacted, lithified to form this limestone. We know that this area was a seafloor, a relatively shallow seafloor. When I say shallow, not shallow enough that you can wade through it, but not the deep seafloor. It's a relatively shallow seafloor for many millions of years, in which this calcareous ooze accumulated, compacted, and lithified. So these are in southeastern England, I think along the coast of the English Channel. See these limestone cliffs. So if limestone forms from calcareous ooze being deposited on relatively warm, shallow seafloors, what about the cold, deep ocean? Well, there's another type of phytoplankton that lives in the ocean, and they make their exoskeletons out of silica. So silicon and oxygen, they make it out of silicon. And whenever they die, their exoskeletons settle to the seafloor too. Whenever they accumulate, they form a sediment called siliceous ooze. Not calcareous ooze, but siliceous ooze. And this siliceous ooze is buried, compacted, and lithified. It forms the biochemical sedimentary rock chert. So you can see the chert here. Chert has this conchoidal fracture where if you break it, it breaks along these curved, smooth surfaces, which allows you to create an edge through a process called napping, where you hit little tiny flakes off of an edge. You can create a serrated edge. So chert was a common tool used to make serrated edges, like in this flint arrowhead. Flint is a variation of chert. So if we find limestone, it tells us that this was a relatively shallow seafloor, that the water was warmer. By warm, I don't mean really, really cold, not tropical warm. And chert means it was like deep, cold seafloor, or also it could have been a polar seafloor. The difference is the temperature of the water. Because what happens is in a cold, deep seafloor, more carbon dioxide can be dissolved in cooler water. And the more the carbon dioxide is dissolved in water, the more acidic it becomes. So, you know, if a can of seltzer is just carbonated water, it has the same pH as lemon juice. It sounds surprising, but it's very acidic because of all the dissolved carbon dioxide. It creates carbonic acid. That's also how we get acid rain, is because we burn fossil fuels, which releases carbon dioxide into the atmosphere. The carbon dioxide dissolves into the droplets of rain as they fall and creates carbonic acid. So the more CO2 dissolved in water, the more acidic it is. And the cooler the water, the more CO2 can be dissolved in it. Well, in the deep sea floor, the water is cool enough that there's a lot of CO2 dissolved in it, which makes it very acidic. And that higher acidity of the water causes the calcium carbonate to dissolve back into the water. So that calcareous ooze, like we see here, it can't accumulate on cold sea floors, like on the very deep sea floor or the polar sea floors near the North Pole or South Pole. It can only accumulate on shallower, warmer sea floors where the water is not as acidic. But in those cold, deep sea floors, the siliceous ooze, which doesn't dissolve as easily, it accumulates and dominates. So that's why we find chert forms in cold or deep sea floors or polar sea floors, and limestone forms on relatively shallow sea floors. So here's a beach with a bunch of shells that have been deposited on it. If these shells are compacted, they break into tiny pieces, and if they're cemented together, it forms it's a variant of limestone called Coquina, where you can see the little tiny shell fragments that are cemented together. It's hard to see, but you can see these clear, milky crystals. Those are quartz crystals. So the fragments of shell are cemented together by quartz crystals. Then another environment is we have these clear, shallow ocean or salty lagoons. And what happens is this isn't very common today, but it was very common in Earth's past a long time ago. But there's bacteria that's photosynthetic, and those bacteria form these structures called stromatolites. So anything that's photosynthetic, that means that it makes their own food using sunlight. And so these bacteria, they need to stay close to land because that's where a lot of nutrients are. And so any photosynthetic organism, like a plant, needs water, carbon dioxide, sunlight, and nutrients. So there's plenty of water, there's plenty of carbon dioxide, there's plenty of sunlight. You just have to stay near the nutrients. So the bacteria wants to stay near the coastline, preferably somewhere where there's not a lot of surf, a lot of waves. So that's why they like lagoons. These bacteria want to stay there. So how they stay there, they excrete a sticky substance, which creates a mat that they stick to, a sticky mat. Well, not only does the microbes stick to the mat, but sediment in the water sticks to the mat as well. Just like if you take a piece of Scotch tape and you adhere it to a surface and then you peel it off and put it on another surface and peel it off, if you do it enough times, it collects enough dust that's no longer sticky. Well, the same thing happens here with these sticky mats. They accumulate enough sediment that they're no longer sticky. So once it's no longer sticky, the microbes have to migrate to the outside of that layer of sediment and excrete a new sticky mat. And this process continues. And so what happens is it develops these nodules of sediment it's all adhered together by that mucus, that sticky mucus that the bacteria excretes. And so the bacteria actually creates these structures, and they're known as stromatolites. And so you're actually looking at the oldest structures made by organisms on the planet, these stromatolites. These are actually from part of Australia, because the first form of life on Earth was photosynthetic bacteria, and they lived in shallow coastal lagoons on Earth, and they made structures just like this. So these stromatolites are being produced by the descendants of the oldest forms of known life on the planet. So if you go back 3.5 billion years ago, this is life on Earth. This and nothing else. Just these bacteria forming these nodules in coastal waters. So now we're going to look at the sequence of sedimentary rocks that forms along an ocean coast in a period of what's called marine transgression, which is rising sea levels, and regression, which is falling sea levels. So I'm actually taking a couple steps back. So let's say that this is, I'm going to draw a cross section. Let me do it. Let me get some black. So this is the surface, okay? And let's say that we have, this is water, okay? So right here is the coastline, right? That's the coastline. That's where the water meets the land. And so this is the sea floor, all this right here. And then here, this is above sea level, okay? All right. So let me just erase that, erase that. So what happens is, what type of sediment is deposited right at the coastline? Okay, well, sand. So we get a layer of sand that's deposited. And what's deposited beyond the sand? Well, sand is larger than mud. So mostly sand and mud are flushed into the ocean by rivers. And so the sand is larger, so it settles out first. The mud gets carried out further. And so we'll make the mud this color. So mud gets deposited out here. And then if you go further out, all the land-derived sediment, the sand and the mud, have been deposited out. And the only sediment that's deposited this far out to sea is the sediment that's being generated by the organisms actually living in the ocean, the phytoplankton. And they produce the calcareous ooze. I'll just use this to make calcareous ooze. Typically give it like this brick-like pattern. So this calcareous ooze is deposited for the route. What happens is then sea levels, they then rise. And so the coastline was there, now the coastline is here. Now the same pattern of sediment deposition continues. You have sand being deposited, and beyond the sand you have mud being deposited, and then beyond the mud you have the calcareous ooze being deposited. And then sea levels rise even more. Now let's say the sea level is right here. Whoop. Nope. Don't want to warm a pen is not. And that same pattern of sediment deposition continues sand at the coastline. And further out, we have mud. And then further out, we have calcareous ooze. So you can see the sand is always deposited in shallowest water right along the coastline. Then mud is deposited in a little bit deeper water further out from the coastline, and then the calcareous ooze is deposited in the deeper water, further from shore. Now, if you go out here and look at the layering of sedimentary rock, say right here, and so as we look at this, we would see layer sandstone on the bottom with mud on top and the calcareous ooze above that. Now the sand, it lithifies into sandstone, the mud into shale, and the calcareous ooze into limestone. Whenever we see these three sedimentary rocks deposited like this, sandstone, and then shale and limestone, it tells us ancient coastline in a period of marine transgression or rising sea levels. As we can see here, you can see the sand at the coast, and then mud, and the limestone. As sea levels rise, the deposition moves inland with rising sea levels. And so, just as we saw, they do a cross section there. See the calcareous ooze, limestone top, the shale, and then the sandstone on the bottom. All right. So that tells us there's been a period of marine regression, rising sea levels. So if we see the layers of, the opposite pattern forms in a period of marine regression, which is falling sea levels. The transgression is rising sea levels, regression is falling sea levels. So if we see sandstone, shale, limestone, shale, sandstone, so we see this layering of sedimentary rock. What does it tell us? Well, this pattern of, I'll use blue for transgression. Every time we see the sandstone, shale, limestone, that was marine transgression, right? Which is rising sea levels. And we see that again right here, right? Sandstone, shale, limestone. Another episode of marine transgression, rising sea levels. If we see the opposite pattern, which I will use green to indicate, or if we see limestone, shale, sandstone, that is marine regression, falling sea levels. We see the same thing here, limestone, and then shale, then there's no sandstone, but you see that pattern, limestone, shale, marine regression. So you see in these layers of sedimentary rock, it's recording periods of time which the sea levels rose and then fell, rose and then fell, rose and then fell. Right now you hear people talking about how the sea level is rising today, right? We are currently in a period of marine transgression where sea levels are rising. And so this pattern is forming across the planet. Sorry, I shouldn't use this pattern, the marine transgression pattern. That pattern is forming across the planet because of rising sea levels. And sea levels have been rising since the end of the last ice age, for the past 20-some thousand years. Sea levels have been rising. But and so because we see these layers of sedimentary rock that alternate back and forth, sandstone, shale, line. It's not always that simple. Sometimes it's more complex. There's layers of coal and stuff in there. Those tell us that sea levels have risen and fallen multiple times on Earth. They're actually always rising or falling. And so sea level rise and sea level fall is a natural process on Earth that's always occurring. So it just shows coming back. One thing I want to say about this is, let's say, rising sea levels. One of the cause of it is, say, climate change or global warming. And that is true, because I said that sea levels were rising since the end of the last ice age. During the ice age, there, as we'll talk about later on in the course, there were large sheets of ice that were covering many land masses. Now, the water that the ice was made up of came from the ocean. So what happens is the climate on Earth cools, and whenever water evaporates from the ocean and it falls as snow over land, it never gets warm enough for all that snow to melt. And so that snow just accumulates year after year on land and eventually turns into ice. That's how you form those glaciers. And so when the Earth's climate is cool, water accumulates in the form of ice on land. And so water is essentially removed from the ocean, and so sea levels fall. Now, as the climate warms, the glaciers begin to melt. And the meltwater flows where? Well, back into the ocean. And as more glacial ice melts, more water flows into the ocean, so the sea levels rise. And so sea level change is directly related to climate change. Rising sea levels mean a period of warming, less glaciation. Falling sea levels mean a period of cooling, increased glaciation. And so the fact that we see rising and falling sea levels in the historical record, the geological record from these sedimentary rocks, tells us that Earth's climate is always changing. It's always changing in the past. Right? And we shouldn't be surprised because everything on Earth is constantly changing. The Earth system, the solid Earth, the atmosphere, the biosphere, and the hydrosphere, they're always changing. Right? And so we get that context from these sedimentary rocks. And so, you know, the concern is, as we'll talk about later, you know, it's not the fact that the climate is warming, it's about the rate at which it's warming. And when we talk about, you know, mass extinctions, we'll see what happens if the climate warms too quickly. You know, if the atmosphere changes faster than the biosphere can change, faster than animals can, or faster than organisms can evolve, well, they die, they go extinct. And we'll see how rapid climate change results in mass extinctions. And that's what the concern is with the rapid climate change that's occurring today. Like we have evidence of it happening, not quite as fast today, but happening in the past. And we see what happens. So we'll talk about that later on in the course. But these are the insights that these sedimentary rocks can give us about Earth's past. And it's not just, you know, obscure knowledge about the Earth. It's directly related to the world we're living in today because it provides context that we can see, oh, this has happened before. This is a natural process. We can see what the natural amount is, and we can see how the Earth responds to it. The other components of the system respond to these different things. So, like I said, it's really important to have a good understanding of how our planet works because it helps us understand this planet, and so we can live in it more harmoniously, live on it more harmoniously. Here's a question, one of my favorite questions. The rock on top of Mount Everest. Now, Mount Everest is, you know, superlative on Earth because it holds the distinction of being the highest point, the summit at least of Mount Everest, the highest point above sea level. So you can't get any higher elevation on the surface of the Earth above sea level than you can at the summit of Mount Everest. Well, whenever people started, you know, going to the top of Mount Everest, someone that was geologically inclined asked the person, well, if you can, grab a chunk of rock from up there. I want to know what type of rock is at the highest point above sea level. Well, whenever they brought that rock down, they were a little bit surprised to find out that it was limestone. Well, limestone, we know, forms in a shallow ocean. And this limestone in particular formed in a shallow ocean 200 million years ago. So what does the fact that at the top of Mount Everest is 200 million year old limestone tell us about the geologic history of the Himalayas, which is the mountain chain that Mount Everest is in? Does it tell us that A, 200 million years ago, the Himalayas did not exist? B, the ocean level 200 million years ago was much higher than today, so that everything was below sea level? Or C, there was a high altitude lake in the Himalayas? Well, rather than just give you the correct answer, I'll discuss why the incorrect answers are incorrect. Well, first of all, there's a high altitude lake in the Himalayas. At that high altitude, it's very cold, right? There's no liquid water. It would be frozen solid. And if it's frozen solid, even if these sort of plankton lived in lakes, not the ocean, the water wouldn't be liquid. They couldn't live there. They couldn't live there and produce the exoskeletons that could be deposited and form limestone. Plus, we know, yeah. So that's basically, I mean, they're a high altitude lake in Himalayas. That's a glacier, right? It's not. It doesn't exist. How about everything was beneath sea level 200 million years ago? Well, if that was the case, that would take a lot of water. But if that was the case, then everywhere we look on Earth, where we find sedimentary rock that's 200 million years old, it should be what type of sedimentary rock? It should be marine sedimentary rock that's deposited on the ocean floor. We shouldn't find any terrestrial sedimentary rock. There's sediments that are deposited on land. There should be no terrestrial sedimentary rocks that are 200 million years old. Well, we not only find terrestrial sedimentary rocks that are 200 million years old, right? But we find those sedimentary rocks that have fossils of land-dwelling organisms in them. So we know for sure that there were locations on Earth 200 million years ago that were above sea level, because they have sediments that are deposited on land, and there's fossils of organisms that live on land in them. And so that leaves A. 200 million years ago, the Himalayas didn't exist, which is correct. So if you can, so the Himalayas exists between India and the rest of Asia. Now formed, and we'll learn this when we talk about plate tectonics, from India colliding with Eurasia, forming the Himalayas. And between India and Eurasia, before they collided, there was a sea floor, an ocean. And so some of that rock that formed on that sea floor got scraped up onto Eurasia, and so that rock was limestone. Whenever India finally collided and the Himalayas were formed, that limestone got pushed up with a deforming rock, got pushed up as the mountains formed. And it just happened that limestone just happens to now be perched at the top of Mount Everest. But I love this question because it really illustrates the dynamic nature of this planet, how a rock that's formed on a sea floor, right, from organisms, the remains of organisms that live in the ocean, and their calcareous exoskeletons accumulating the seafloor, find how a rock that forms in that environment could 200 million years later find itself at the highest point above sea level, covered by snow and ice. And like, how much more extreme change can you get than that? It's just such a dynamic planet. And 200 million years isn't even that much time with respect to Earth history, right? 200 million years is 0.2 billion years. Now, 0.2 is a relatively small amount out of 4.6. Right? So 4.6 billion. So it's just remarkable the amount of change that occurs on this planet. So finally, we'll leave off with fossils. Let's talk about fossils briefly. We'll talk about them more in depth later, but if we're going to talk about sedimentary rocks, it'd be amiss if we didn't at least mention fossils. So here we can see examples of fossils. We already saw this image of the limestone, of the fossils of snail shells and clam shells in it. We have other fossils here. So this is a crinoid, which was an animal that lived on the sea floor, and it was a filter feeder, so it filtered food out of the seawater, very similar to like a sponge today, or tube worms today. And some of you might recognize this. This is a trilobite. So this was like an arthropod, like a same. You can think its closest living relative is a horseshoe crab, which I'm sure you can kind of see that resemblance. But these live, quite some time ago. 500 some million years ago. But these are all examples of fossils, and there's many different examples of fossils. They call them fossils. So of these three organisms, which of the following animals leaves the best fossil record. Okay, in other words, it's the easiest to fossilize, so we find a lot of fossils of that organism, or a very abundant number of fossils of that organism. Well, as we'll learn, to be fossilized, you have to be basically buried and preserved in the rock. And that all has to happen before the structure of the organism is destroyed. Well, how are most organisms destroyed? Well, they decompose, they're rot. They're either that, or they're scavenged and eaten by larger organisms. So let's say if a deer dies in the woods, it's going to be scavenged by animals, like some coyotes and other animals, and then mice and whatsoever, and then the rest of it decomposes by microbes and fungus eat it. And so the deer's gone. It's not fossilized. And so you think an animal like this is an Archaeopteryx, if it died, it's likely not going to be fossilized because it's not going to last long. Its body parts are going to be consumed by either larger animals or microbes and fungi as it decomposes. And if that's true for the Archaeopteryx, it's especially true for the jellyfish, which has no hard tissue at all. At least the Archaeopteryx has bones, right, that might last a little bit longer and might have a chance of being buried and preserved before they are destroyed. But a jellyfish, the chances of a jellyfish not decomposing and being preserved are very small, since it's nothing but soft tissue. On the other hand, the clamshell, it's made of calcium carbonate, right? It's not even an organic molecule, calcium carbonate. You can't eat that. Nothing's going to eat it. The only way it can be destroyed is if it slowly dissolves back into the water, which, as I said, happens slowly. So the chances of a clamshell actually being buried in sediment and being preserved and fossilized are fairly good. And so for that reason, we find a lot of fossils of these hard structures that are not made up of organic matter. So you may think, well, bones are hard, aren't they? They are, but bones are also made up of collagen. What was it? Collagen and other materials that are organic, right? So they can be eaten, right? They can be decomposed by bacteria and other microbes. So, but where calcium carbonate, it's not organic. It's not food. It's not a carbohydrate. So it lasts a long time and it's most likely to be fossilized. And so most fossils we find are of these hard structures produced by organisms, shells and exoskeletons. So the exoskeleton of the trilobite, the hard structures of the crinoid, the shells of snails. Here's a shell of an organism called an ammonite, which is a type of cephalopod. Its closest living relative is the nautilus. Other cephalopods that don't have shells but alive today are cuttlefish, squid, octopi. Then we have bivalves like this clam, and then this is a brachiopod. Brachiopods were once very common, but they're not very common today. So most fossils we find are not of Tyrannosaurus rex or Brachiosauruses or Velociraptors, though we do find those fossils. Most fossils look like this, right? Because these organisms have hard structures that last a long time, that are more likely to be preserved and fossilized. And so most of the paleontological record is of organisms like this, right? So which type of rock are fossils most likely to be found in? Igneous, sedimentary, or metamorphic? Well, igneous rock forms from molten rock solidifying. So in order for an organism to be preserved in igneous rock, it almost have to fall into the molten rock. And then the molten rock would have to solidify around the organism. Well, molten rock is anywhere between 800 to 1200 degrees centigrade. And at those temperatures, any organic tissue, organic matter is just going to combust and burn. So we're not going to preserve any parts of an organism in molten rock. So we don't find any fossils in igneous rock. Metamorphic rock, the rock is altered by heat and pressure. So even if the original rock had a fossil in it, the process of metamorphism will destroy the fossil. So we don't find fossils of organisms in metamorphic rocks. The type of rock we do find fossils in is sedimentary rock. So what happens is the organism is buried in sediment, and it happens to be preserved, and then over time the organism is fossilized, and the sediments around it are lithified. So then we find the fossil in the sedimentary rock. So if you want to look for fossils, you need to look in sedimentary rock. So sedimentary rocks, they provide us information about the environment and processes that were present when the sediment that those rocks are made up of were deposited. And so sedimentary rocks tell us about the environment. Remember I said, sedimentary environments have characteristic types of sediments. Those are sand, beaches have sand. Glacial environments or the base of mountains have, poorly sorted gravel, form conglomerate. So the type of sedimentary rock gives us information about what sort of environment it is. And as we talked about, there's also clues in the sedimentary rock, like ripples and so forth, that can give us more information about what type of environment it was in the past. So when we find sedimentary rocks, we're getting a glimpse into what was the environment like millions of years ago at this location. And if fossils are present in the sedimentary rock, they also provide us information regarding the life that was present at the time that those sediments were deposited, which is even more wealth of information. So sedimentary rocks, they play a key role in investigating Earth's past. That's why they're so important in historical geology. So we focus a lot on sedimentary rocks in this course because of the information they provide us. We do talk about igneous metamorphic because they have information in them too, but not as much as sedimentary rocks. Right? We're not going to figure out if a place was a desert, a lake bed, or a sea floor from igneous metamorphic rocks. We can tell if there was a volcano, if there was certain tectonic activity from igneous metamorphic rocks, but we're not going to know what type of environment it was. And we're not going to know what type of life was present. So we focus a lot on sedimentary rocks in this course because of the wealth of information that they contain. And so in the sedimentary rocks lies the secrets of the Earth. And therefore, the story of our planet and the story of us.